Alright guys, so today we're going to talk about special right triangles. And the first special right triangle that we're going to talk about is just your regular old right triangle. And so what makes it a right triangle is that it has one right angle, or a 90-degree angle. And the first special right triangle we're going to talk about is just regular old Pythagorean theorem, where you have A and B, and A and B really doesn't matter. The one that does matter is what you label C. C is always going to be across your 90-degree angle, or it's always going to be your longest side in a right triangle. And so from Pythagorean, we get a squared plus b squared equals c squared. Now, if you're looking for c, c is always going to be equal to whatever a squared plus b squared is. And if you're looking for a, and again, this can also be b, is going to be c squared minus b squared. And where a and b, oops, forgot to square that, where a and b can be switched. Alright, so that was just regular Pythagorean theorem. That's when you don't have any angles, you can't use any special right triangles. And what I mean by that is brings us to the first special right triangle. Now, once again, it has to be a right triangle. From there, if they give you more information, like for example, if they're telling you that one angle is 30, because we know one is already 90, then we can always find that third angle. And so here we have our first 30, 60, 90, and we have to label it a specific way. The one thing that's always going to be true, no matter how you draw your angles, or sorry, how you draw your triangle, is what goes across your angles. And so across 30 degrees, you're always going to label that side x. Across, we'll do a different color, across 90 degrees, or your longest side, it's always going to be 2x. And across your 60, which is kind of like in the middle, it's always going to be x square roots of 3. And that's always true as far as labeling the sides. That's always true for a 30, 60, 90 triangle. The other right triangle that we have is what we call a 45. Now for this one, we got 45, 45, 90. It's also sometimes referred to an isosceles right triangle. And so what we need to know about this is that it has two sides that are congruent. It's a right triangle. And if that's 90 and these two sides are congruent, that means these two angles are also congruent, which is telling me that that's 45 and this is 45. And so when we label it, just how we labeled the other one, the 30, 60, 90, we're going to label this one for the 45, 45, 90. So across the both 45s, or the two congruent sides, we're going to label it x and x. And for the hypotenuse, or in other words, the one across the 90-degree angle, or your longest side, is going to be x square roots of 2. So before we continue, I want you guys to take a look at this right here. So here I have an equation, and notice where the x, or in other words, what I need to solve for is in the numerator. It's on top. So whenever we're in that situation, what the number that's in the denominator, you bring it over and multiply it in the front. So what this would look like is whatever 5, or x would equals whatever 5 times 3 is. Now, that's going to be important once we start doing some of these problems. Now, the second situation is, well, what happens if x is not in the numerator and is actually in the denominator? Well, whenever x is in the denominator, instead of multiplying it over, we're going to switch the denominator, the x, with whatever's on the other side, and we're going to switch them. And so what that would look like is 3 over 5 equals x. Again, that's going to be important once we start doing some of these problems. So moving on. Here let's pretend that you have a friend that's in an airplane, he's flying, okay, and you're down here, and you guys, because you have like 1,000,000 to 1 vision, you guys make eye contact. And so this right here is what we're calling your line of vision. That's kind of what's connecting both of you two. And so when whoever's in the airplane, your friend, when he looks down, he's gonna start by looking straight, which is kind of like his horizontal line, or his line of vision. That's where it starts. It's kind of like his degree 0. And when he looks down, he creates this angle, which we call angle of depression. And kind of the same situation for you. You don't start by looking vertically up. You're going to start by looking horizontally, and then you look up. And so you also create an angle, and that angle is what we call angle of elevation. Now, let's do a little geometry here. Notice how these two lines right here, if they're both horizontal, that means they're both kind of at 0, which means that these two lines are parallel. And so if these two lines are parallel, and this right here represents your line that's connecting, that's kind of like your transversal line, which is telling me some key information about these two angles, my angle of depression and angle of elevation. If we think back when we were talking about angles, because we have two angles that are alternate interior to parallel lines, we can conclude that my angle of depression is going to be the same, or is going to be congruent to the angle of elevation. And so that's going to be important, because whenever we start drawing, or we start getting into some of these application problems, when they're giving us the angle of depression, we can remember that it's the same thing as your angle of elevation. And here comes good old SOHCAHTOA. Okay, so remember, SOHCAHTOA stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we're going to do one example of how we label things. So once again, in order for me to use trig, it has to be a right angle triangle, or a right triangle. And you normally are going to use trig whenever you're looking for a side. So I'm just going to put it up here, looking for sides. And so in order for me to use trig, first I have to have what we call an angle of reference, which I'm going to call theta. And so if this is my angle of reference, if that's the angle that I'm going to use, then across your angle of reference, in this case theta, I'm going to label it as the opposite side. Across your 90 is always going to be your hypotenuse, and next to your angle of reference is what we call the adjacent side. And so if I want to define sine theta here, sine is going to be opposite over hypotenuse. Cosine of theta, so same angle of reference, now we're dealing with cosine, is going to be adjacent over hypotenuse. And lastly, we have tan, or tangent of theta. So again, same angle of reference, just different function, is always going to be opposite over adjacent. And that's always true. We always refer back to these three equations: sine, cosine, and tan. And it's always going to be sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent or tan opposite over adjacent. That is always going to be true. And we use these functions whenever we're looking for a side measurement. So moving on. Now, in this case here, I once again I have my angle of reference, and so if that's my angle of reference, I still label it as follows. So across my angle of reference, I have what we call the opposite side. Then we have across my 90, I have my hypotenuse, and then my adjacent. Now, sometimes you're gonna have some problems where x, or what you're looking for, is actually your angle of reference. So in this case, we're gonna have to be looking for an angle, and so everything. So in other words, so if you were to set up your equation, you would have sine of x, because that's my angle of reference, and you would get it to be opposite over your hypotenuse. If you were to set up cosine, same thing. You would get adjacent over hypotenuse, and then tan of x would be opposite over adjacent. And so here's our original equations that we would start with. Now if you notice, because x is inside my function, I somehow got to get it out. I somehow got to cancel this sine, cosine, and tan. And so to do that, we use what we call the inverse. And so the inverse, if I apply the inverse to each one of these, I would get x, or the angle. And in the calculator, I would be inputting the inverse sine, and then whatever the opposite side over the hypotenuse side is. Same for cosine. If I wanted to get my angle, I would use cosine inverse, and then whatever the adjacent side over the hypotenuse. And lastly, same with tan of x. If I wanted to solve for the angle, I would simply put tan inverse, and then whatever the opposite side over the adjacent side is. And we use trig inverses whenever we're looking for angle measurements, and we're given two sides. Now, depending on what calculator you have, you might see it as sine inverse, or you might see it as arc sine, and etc.